Imagine we could leave Earth behind. Not for Mars, not for the outer planets, but for nearby stars, within a few dozen light years. The galaxy stops being an abstract map and becomes a neighborhood, filled with worlds that don't fit our instincts. First, Gliese 12b, roughly 40 light-years away, an Earth-sized planet orbiting a red dwarf. A place where daylight may never look like daylight at all. Then, farther out at about 48 light-years, Gliese 1214, be a planet that may be something even stranger. An ocean world, wrapped in a thick atmosphere where the surface could be water and the depths could crush every familiar idea of biology. These aren't just destinations, they're two different answers to the same cosmic question. What does a habitable world really mean? Part 1. Arrival at Gliese 12b, a Falera size under unfamiliar. Size under spacecraft slips into the Gliese 12 system. The first shock isn't the planet, it's the star. A red dwarf doesn't shine with the sun's warm white gold. Its light is deeper, more saturated, leaning toward crimson. Not dramatic like neon, more like a constant muted red glow that changes how everything looks, including the sky. And red dwarfs have a special kind of patience. They can burn for tens to hundreds of billions of years, vastly longer than the sun. If life gets a foothold near a stable red dwarf, it may have more time than Earth will ever get. Gliese 12b appears close to Earth in size, and current estimates suggest its surface gravity might be broadly comparable, not crushing like a massive super-Earth, not disorienting like a low-gravity moon. If you could stand there, your body might feel surprisingly normal, but the environment wouldn't. Under red dwarf light, the color palette of the world changes. The sky could be darker orange, rust, even brownish depending on the atmosphere. The ground would reflect red heavy light in unfamiliar tones, and if photosynthetic life exists, it likely wouldn't be Earth green. Plants on Earth evolved to exploit sunlight filtered through our atmosphere. Under a red dwarf, biology might pivot toward pigments that absorb more efficiently in that spectrum, deep reds, purples, or near black surfaces that drink in what little energy arrives. So does Gliese 12b have a solid surface? Its measurements are consistent with a rocky world or one dominated by a rocky interior. That matters because rock implies geology, mountains, volcanism, chemical cycling, the machinery that can stabilize climate over time. And if it sits in the right temperature range, liquid water becomes possible. Not guaranteed, but plausible. Maybe lakes, maybe shallow seas, maybe oceans broken by land. A world like this can sit on a knife edge. Not fully dry, not fully drowned. Part 2. The tidal lock question. One-stide day. One-stide Nate. There's another twist common around red dwarfs. Tidal locking. Many close-orbiting planets end up with one face turned permanently toward the star in eternal day side, and the other turned away in eternal night. If Gliese 12b is tidally locked, it becomes a planet of extremes, a hotter, brighter hemisphere under constant red sun, a colder hemisphere in endless dark, and between them, a narrow boundary, the Terminator Zone, an eternal twilight ring where temperatures could be most moderate. If humans ever imagine visiting, that twilight band is where possible would live if it exists at all. Not because it would be comfortable, but because it's where physics sometimes compromises. Gliese 12b, in other words, is a world that still feels adjacent to our intuition. Rock underfoot, gravity you recognize, a surface you can imagine mapping. Now compare that with the next planet. Part 3. Gliese 1214b. Waiter isn't a featured, it's the wall planet. Gliese 1214b's looks nothing like Earth. Once you run the numbers, when scientists estimate its density, it comes out too low for a simple rock and iron planet. Something lighter must make up a large fraction of its bulk. The leading candidate is water, a lot of it, not blue oceans and beaches. More like a planet where water could represent a significant fraction of the entire world, possibly cloaked under a thick, opaque atmosphere. Spectra suggest an atmosphere that may include water vapor, and possibly hydrogen and other molecules, creating a world where the surface is hidden and the boundary between ocean and sky is nothing like Earth's. This is the crucial shift. An increase of only a few Earth masses can push a planet into a very different regime, one where water becomes dominant and the planet's geology is sealed under pressure. On Earth, the surface and the interior talk to each other constantly. Volcanoes outgas, rain draws carbon down, rock weathers, plate tectonics recycles material, oceans buffer temperature. That conversation stabilizes climate over long time scales. On an ocean planet, that conversation can go quiet. If the ocean is deep enough, the rocky crust may be isolated beneath layers of water and high-pressure ice, cutting off the familiar carbon silicate thermostat that helps Earth stay temperate. And yet here's the irony, this alien arrangement may still be stable for a very long time. A thick atmosphere can redistribute heat, a massive ocean can act as a thermal reservoir, and chemical energy may still flow from the interior, even if rock and air rarely meet. Part 4. The Pressure World. Oceans, how deep they change the phase of water. Now picture an ocean not a few kilometers deep like Earth's, but tens or hundreds of kilometers. Down there, pressure doesn't just increase, it transforms matter. Water can enter exotic high-pressure ice phases that don't behave like surface ice. In some models, you can get layers where water is hot, compressed, and structurally reorganized states we can barely reproduce except in labs. And that pressure changes the biological rules. Rigid structures, bones, shells, large air-filled cavities become liabilities. Life, if it emerges, would likely favor soft, compressible bodies, minimal void spaces. Slow, efficient motion forms closer to what Earth's deep ocean hints at, but taken to an extreme, light would be scarce. Even on Earth, usable sunlight fades fast. Beyond a couple hundred meters, it's mostly darkness. On a world with a thick atmosphere and deep global ocean, the majority of the biosphere, if it exists, could be permanently night. So where does energy come from? Not from sunlight. From chemistry. Life could run on reactions involving hydrogen, methane, sulfur compounds, or other chemical gradients powered by geochemistry, not starlight. In such environments, eyes may be optional, while senses tuned to pressure, vibration, temperature, and chemical traces become essential. Communication might be chemical, or mechanical signals carried by currents and pressure waves through water, traveling far in a dense, quiet world. And if there is light at all, it may be life-made. Bioluminescence, not as decoration, but as language, brief flashes and patterns that mean survival. Part 5. Two worlds, two destinies. Hey beetle doesn't he's Pito Bulzen. The Pridne for use, put these planets side by side. and the contrast is sharp. Gliese 12b is the almost familiar category, likely rocky, potentially temperate in the right region, with surface environments that could create many niches, a world where geology and atmosphere may still interact in Earth-like ways. If life appears there, it could start small, microbial, localized, stabilizing in protected environments, evolving slowly under a red sun. Gliese 1214b is a different category entirely. Water-dominated, high-pressure, deep ocean physics. A surface that may not offer land, shorelines, or anywhere to build a biosphere that could be extensive and still utterly inaccessible. This is the point that matters. A planet can be habitable in the cosmic sense, stable, energy-rich, chemically active, and still be uninhabitable for humans. For us, habitability usually implies ground, manageable pressure, and a place to expand. An ocean planet doesn't offer that. Even advanced technology would be fighting the environment non-stop. Pressure, corrosion, isolation, the absence of stable land. You might visit, you might sample, but building a civilization there would be like trying to colonize the crushing depths of Earth's oceans. Except the ocean is the whole planet, complication. The bigger lesson, these worlds force a humbling shift in perspective. We often search for a second Earth, as if the universe owes us a familiar shoreline, but nature doesn't optimize for comfort. It optimizes for what physics allows. Ocean planets may be common, rocky, Earth-like balances may be rarer than we want to believe, and life, if it's out there, may most often thrive in places we can detect only indirectly, through atmospheric hints and faint spectral fingerprints. So the real question isn't only, where can humans live? It's, how many different kinds of living worlds can the universe build? Gliese 12b and Gliese 1214b are more than points on a catalog. They are a reminder that life could be widespread and still not meant for us. And that makes Earth's thin, fragile balance of land, ocean, air, and sunlight look less ordinary and more like a once-in-a-cosmos kind of gift.